Okay, hello, welcome back. So we are continuing with rotating frame analysis. We looked at positions. We can write position of an arbitrary point B to in the base frame to be position of a known point A in the base frame from the relative position of B relative to A as observed from this observer. We took the derivative, we came up with the velocity equation, and velocity of B in the base frame is velocity of A in the phase frame. And you have a bunch of other terms. The first one is what velocity of B relative to A is what observer measures directly. And the last term, omega cross R, is the effect of the rotation of the observer itself. Now the last bit here is the acceleration. I can take derivative of the velocity equation. D over dt of V of B is d over dt velocity of A plus d over dt of this term, V of B relative to A xyz, plus, and the last one is d over dt of omega cross R plus omega cross d over dt of R. Okay, lots of terms. I'm not going to derive it like last time. The derivation is in the textbook. But what I'm going to do is give you the final answer and discuss what those are. So the first term is, oops, where did it go? The first term is the acceleration of B in the base frame that we are trying to find. The next term is the absolute acceleration of A in the base frame. The next term, let's call it relative acceleration of B with respect to A as measured by XYZ. So this is what the observer really measures with their tape measure or whatever. And these last terms come out into three terms. The first one is omega dot cross RB relative to A. And this omega dot is the acceleration, the angular acceleration of the frame. We are not going to introduce a new term for angular acceleration. Remember, alpha was already used as angular acceleration, but it was for the kind of convention was for the angular rotation of the body itself, not the frame. So for simplicity and without introducing a new term, let's use big omega dot. And we have two more terms coming out of essentially the last one. It is going to be omega cross R. And finally, this term, omega cross V of B relative to A, as observed, all of these vectors. So many terms. Let's, let me do this because I need this space. This one is what we are trying to find. This is the absolute acceleration of B in Y capital. in base frame. This one is absolute acceleration of A in base frame. This one is relative acceleration of B as measured by A who is moving and rotating. Note that. This term, note omega dot is essentially the angular acceleration. This is the effect of angular acceleration of the observer Note the similarity of this with the term we had before, alpha cross r. It is in a sense same type of acceleration. This term is, let's call it effect of angular velocity of observer. Again, note its similarity with that omega squared times r that we had. It is in some sense related to that centripetal type acceleration. We have two omegas and one r multiplied to each other. And because of that, you expect to have some form of centripetal-ish acceleration. And this one, the last one, we had seen a similar look of it before. This is Coriolis acceleration. That is the combined effect of both rotation of the frame and this relative movement inside that frame. If both of them exist, you have this Coriolis effect that must be compensated. All right, good. A lot of things, but all of them kind of make sense that you expect them to show up. If you have angular acceleration of the frame, you expect that term to show up. If you have angular velocity, you expect some centripetal type acceleration to show up. And finally, if you have both angular velocity and linear velocity, you expect some Coriolis effect to show up. And I'm really running out of space, but let me finish up here. And the point I want to make here is that none of it is really new. You had seen all of it before. Remember when we were talking about polar frame again? Polar frame. We had acceleration A in the polar frame, essentially this relative type. It was r double dot minus r omega squared in the radial direction plus r theta double dot plus 2 r dot theta dot in the other direction, transverse. And these are exactly what we have now. This one is the equivalent of relative acceleration. So this is A of B relative to A. This one is the Coriolis, the centripetal that we have below. This one is omega dot cross R. And the last one is Coriolis 2 omega cross V. V of B relative to A. I don't have a space to write it. So all of these exist. All of these are acceleration in a polar frame that then are added to the acceleration of the frame itself to give you acceleration of B in the absolute frame. All right, all good. So a very, very, very long, this is the longest equation of this textbook. We have 1, 2, 3, 4, 5, 6 terms in this equation. But the concepts, none of it is new, and the formulation is just a generalized and slightly different notation of what we had before. So that is all I have for this section. Let me see if there is anything else I need to say. No. So this formulation, I just want to add this. I'm not going to write anything down. Let me box them. This, and let me see if I can do this. These three equations are the most general way of relating motion of one point to another, and it works in any situations. Doesn't matter whether you're dealing with a rigid body, whether you're in 2D or 3D, the same formulation always works, and you can always reduce this set of formulations to existing ones. For instance, I don't know whether I should say this. I don't have a space to write anything down. No, I don't write it down. But you can reduce this, for instance, to translational frame equation that we had before, noting that in that case, you will not have any velocity, relative velocity. So all these V of B relative to A in XYZ would be 0. A would be 0. And in that case, your omega would be the angular velocity of the body itself. And you recover the same set of equations. So this can be converted to anything you have seen so far. All right, I'll leave you with this giant equation. You will see its usefulness and its power in solving a variety of problems in class. So that concludes this chapter. I'll see you in the next chapter.